Good evening. Welcome to the inaugural program of the series Aspen Science Highlights. I'm Coleman, and my guest is Ajay Gopinathan of the University of California, Merced. Ajay is here in Aspen as part of a seminar series at the Aspen Physics Center, and we're fortunate and wish to thank the Aspen Science Center for doing a children's show at which we got to see Ajay's presentation, which we thought was quite interesting for adults as well. And also his work includes graphical information, which should be very interesting to watch here on Grassroots Television. Ajay, you're a biophysicist.
That's correct.
I used to think biophysics was sort of how the eye works, things like that, but I guess it's gone much further than that.
Yeah, I would sort of agree with you. How the eye works is actually an important part of biophysics. There's a lot of active research on optics.
That goes back many years.
That goes back many years. And so biophysics has a long history, and its definition depends somewhat on who you ask. So, but in my view, biophysics is the study of biological systems using physical principles and techniques. So if you think about it, this goes back to when you said Watson and Crick were looking at DNA, using X-ray crystallography, using patch clamp electrical measurements to look at squid axons
Watson
and neurons.
Crick discovered that DNA is actually what controls heredity and genetics.
That's right. That's correct.
So and that did involve deep physics.
That's right.
Crystallography goes back into fundamental physics.
Right. And so that has now translated into cryo-electron microscopy, super resolution microscopy, where you can see things in great detail.
But in your case, it doesn't take highly sophisticated instruments to see some of the phenomena.
That is correct.
Because what you're working on, and which we were happy to see when you presented it to the kids at the Physics Center last week, flocking and swarming of birds, fish, locusts. We can guess what that has to do with physics, but let's look at some examples of what flocking. I particularly like the ones with flocks of starlings, because the shapes and the changes are so dynamic. It looks like there ought to be a physical law describing it, but I guess, I mean, look at that whole flock moving as if it was a single organism.
That's right. And so this is a classic example of flocking, and that's probably been viewed like 2 million times, but it's just so beautiful.
Oh, yeah.
The patterns that they make.
Now those just look like birds flying around.
That's right. But then wait till it gets denser and denser, and now you begin to see this collective emerge.
Right. Well, that's again a sort of a, if not real physics, an analogous thing where the phenomenon doesn't occur until a certain density of the principal fundamental objects, the birds.
That's correct.
Until you have enough birds, it just looks like birds flying around. But when you have enough, you have phenomena such as this, which is
it's just truly remarkable. It's as if
really
they're dancing. And so that's, as you mentioned, this is one of the deep connections to physics. And so this happens, for example, with locusts as well.
Do we have video of locusts?
Yeah, we do have video of locusts.
Well, let's see this just a little more, because I think...
So you can see that there are parts of the flock that are moving one way and another. And one of the most interesting things that you'll notice about this is that the turning. So they do these coordinated turnings. And sometimes when you have predators, or hawks, or falcons attack, and then they split across and move around them.
And of course, the thing that creates great curiosity in my mind is how the birds on this end can respond to something that's happening on the other end so rapidly and so coherently.
That is correct.
And do you know?
Yeah, so this is one of the interesting questions that gets physicists all excited and hopping about, because this is reminiscent of certain systems that we study in materials, like magnets. So magnet is a very good example. So if you take a piece of iron and you could magnetize it, and it's at very high temperature, you would actually have the magnet is composed, you can think of it as composed of tiny, tiny atomic magnets. And if you're at very high temperature, all these magnets, tiny atomic magnets, are pointing in random directions. And so you don't have a magnet.
So when they're that way, a piece of
It's
iron is just a piece of iron.
But
Yeah.
if you lower the temperature, you can get it to actually get all these atomic magnetic spins pointing in the same direction. And that's when you get what's called a permanent magnet, a fridge magnet that you can stick on your fridge.
But nothing that elaborate dynamically, or
So
can you?
the mathematics. So physicists have studied the system, and it's a very interesting system where the individual interactions. So these atomic spins, they only see their neighbors.
Right.
But somehow there's a collective response, and the whole magnet decides to point in a single direction.
Each in this case, we'll talk about birds. If they're like magnets, each bird really only knows about the few birds right next to it.
That
And
is
yet, each knowing its immediate neighbors can propagate into a macro phenomenon.
that is exactly right.
But
It's a very intriguing question, because even now people are not completely sure. So I think I made this analogy before. It's like if you're a human and you're playing a game of telephone. So you have a bunch of people, and I say something to you, I whisper it to you, you whisper it to the next person, and it goes on. We all know what happens at the end. You get some ridiculous contortion.
It's a party game, and
That's right.
It gets very funny because you might
Yeah.
say something quite reasonable to your neighbor, but by the time that it gets to the end, it could be totally wacko.
But in starling flocks, for example, there are these things called, people have actually studied them. There's this Italian physicist, he went up to the rooftops of the museums of Rome and actually made video recordings of these starlings. And what they discovered is that, unlike how information propagates in this game of telephone, in a flock of birds, there's actually something called scale-free correlations.
Scale-free.
Which means as the size of the collective expands, the fidelity of the information that's propagated doesn't fall off. Okay, it still continues to be transmitted with equal fidelity to the ends of the flock.
And that sort of demands an explanation, doesn't it?
That demands an explanation, and people are trying to adapt these theories that are similar to the theories of magnets, and with other theories that are being used to describe fluids.
So when you do have a theory with the hardware that you have, you can produce a video that really shows what the theory would predict a swarm would behave like.
That is correct. Yes.
Do you have someone we can
Yes,
look at?
actually we can. And so this is from actually my own example, but there are others that I can show you.
Yeah.
But this is talking about, so I should mention that it's not just flocks of birds and even locusts, but we also look at, this is a phenomenon that applies across scales. So things like bacteria do swarming. Okay. Even inanimate, in a sense, inanimate objects like protein filaments on a surface with little molecular
This could
motion.
have medical implications, because I understand that bacteria, when they're by themselves, are, in some cases, they're not so dangerous. It's only when they work in concert.
Yeah.
So if we could just screw up their communications,
Yes.
that would be a new field of antibiotics.
Yeah, so biofilms, for example, is a collective phenomenon where a lot of bacteria come together. And biofilms are responsible for a lot of the health issues.
Sure.
They foul up medical equipment, in hospitals, the transmission of diseases and so on.
Sure.
And so, messing with that communication, messing with the formation of these biofilms is actually, this is a kind of research.
Yeah.
gives
So
us
show
insight.
us what a simulation looks like. I mean, it won't be as impressive as a true flock of starlings, but but it is impressive in that it's all done mathematically.
That is correct. And so what I'm going to show you here is one of our own simulations, but this is a cluster of cancerous cells.
Oh, okay.
So this is the cancerous cells on the right-hand side that you see moving around, and you can see that they form these little
Let's see that again.
Yeah.
So this is the simulation.
This is the simulation.
These are cancer cells grouped together?
Grouped together.
And act in concert?
Yeah, so when you have a malignant tumor, sometimes what happens is that they form these little motile groups. And they actually have even leaders, and then they follow them out. And this is how your cancer metastasizes. So
I had no idea.
Yeah,
I
so-
thought it was individual cells that happen to...
they do come out individually, but they also form these kinds of clusters. So
It's a very strange thing then that parts of your own body, if you're a victim of cancer, conspire, not just randomly, but collectively and in an organized way
That's true.
to do you in.
That's true. But this is somewhat hardwired into you because when you develop
Yeah.
from a fetus,
Yeah.
right? When you're
Oh,
an
I see.
embryo to a
So
fetus,
they take over a system that would ordinarily be beneficial.
yeah, in some sense, yes, that's right.
I see.
Yeah, it's motility of these things gone haywire.
Okay, so you're not just talking about birds and interesting mathematics. I mean, this work actually could have serious implications
That's
for
correct.
human
And
health.
So yes, indeed, and we also, in fact, in our lab, we are actually working with robots, and so this is another area where you can think of applications.
Do we
so
have
you've
some
heard
video
of
of-
drones? Yeah. That's
Oh,
right.
let's see.
So let me show you. This is from a different research group, but these are the kinds of
I know
robots that
that's
we
very
use.
tough. There's
Yes,
some
that's from
school in Massachusetts, I think.
yes, some
Harvard.
school,
I
yes.
believe, yeah.
And so this is yeah. So these are what are called little kilobots, and we have
Individual robots.
individual robots, and they're capable of communicating with each other and doing all kinds of neat things. So, for example, here, what you have is there's a gradient of light. So there's a light source here,
Yeah.
and what they're doing is they're moving towards the light. And so
Okay.
you can get them to do these kinds of things. You can get them to talk to each other. And so this is, you're switching the light, and you can see
Yeah.
them. And you can see that they're sort of behaving
They have a
like a
sort
swarm.
of a collective
Right.
behavior.
That's right. And so the idea is that these kinds of, you've heard of drones, and
Oh,
so
yes.
people have been using drones, and so I can show you another video of these drones. Let's see. So these are drones, okay? So these are
Okay.
flying quadcopters, and you can see these actually are communicating with each other to
Uh-huh.
form these kinds of patterns. And so
Okay.
there's no overall central control. It's just
Right.
autonomously, they have a set of rules programmed into them. They talk to each other, and they form these kinds of patterns. And it's a very interesting system, and this is actually done by a Hungarian physicist who, in fact, was one of the founders of the mathematical connection between kind of magnets and flux. And so he
Okay.
developed this theory in the early 90s, and it's called the V-check model. And a lot of
V-check.
yeah, his name is Thomas V-check. So,
And what sort of mathematics is it? Is it just raw statistics?
so
or
he actually
control
developed this
theory? Or?
Yeah, it's actually a set of rules, and so you do what are called agent-based simulations. So you consider a set of particles. Each particle has either you can think of it as a spin, like in your atomic magnet,
Yeah.
or you can think of it as in a flock, a direction in which it is moving. And each agent or particle just looks around, looks at all its neighbors, and decides on a consensus direction and chooses to go in that direction. And so that simple set of rules allows all this rich set of collective behaviors to emerge. In the
Well, it's
system.
sort of reminiscent of cellular automatons, the game of life,
Yes, indeed.
where you can get fantastic
That's right,
patterns
that's right.
based on very simple rules that
yes, that's
dots interact with each
That's
other in a
right.
computer.
That's right. Yes, and there's a deep connection between those two. Yes,
Yeah.
that's correct.
Okay, let's see some locusts.
Yeah, so Locust is a very interesting system. In fact, what is interesting about the Locust is actually they have a morphological transition. They actually change their coloring and their aggressiveness when they go from a species
Oh.
of short-horned grasshoppers to locusts during times of
I see. So they're not just swarming; they're actually going through parts of their life cycle.
Yeah, and so this happens when you, after a period of drought, you get a lot of rain, there's a lot of food, they
Yeah.
begin to aggregate. And when they aggregate, they not only change behavior, they also become more gregarious. So
I see.
typically they are loners, and now they become gregarious.
Okay.
And it's a very interesting thing.
This is in Africa.
Yeah, that's right. So this is in Madagascar, actually. So
Madagascar.
this is a few years ago. They had an immense. So these are miles long. Okay, so these are
We're talking
swarms.
billions. of
Yes,
them.
billion. So that's at this point again it becomes, kind of astonishing that
They can devastate whole crops in
that's
no
right.
time.
That's
look
right.
At, look at
Yes, that's exactly right.
that.
And so
Go ahead.
yeah, it's financially a huge loss to have locusts around, but it's from a physicist's point of view, it's a beautiful system.
It's
again.
very interesting. Yeah.
And I should mention that that a scientist at Princeton once did these experiments because nobody really knew what rules these were that were governing the
Right.
interactions between these locusts. And
Right.
so what he did is he took a bunch of locusts and put them into a circular arena
Yeah.
and then just filmed them.
Yeah.
And then nothing much happened. They would go around in random, and he kept increasing the number of locusts.
Yeah.
And at some critical point, when the density was high enough,
Yeah.
they actually formed an ordered army
okay.
that's going around in like a vortex.
But how can each locust know how many there are in the whole swarm?
That's right. That's right.
I mean, if he could be sitting next to 10 neighbors,
Right.
but that's only 10. That's not
Yes,
enough.
exactly right.
So
And
there must be secondary effects of it's very.
it's essentially the propagation of information. So I have you as a neighbor, and you have the next person as a neighbor.
Right.
And if you have enough neighbors, so for example, in the starling flock that I was talking about earlier,
Yeah.
they actually managed to, looking at the correlations in the speeds and directions,
Right.
they managed to figure out that each starling was looking at about 7 other starlings.
Oh, okay.
So you don't need a large number in order to do this. All you need is that this information be able to propagate.
Right.
In the situation of, but what these rules are, differ from
Well, for
species
it to propagate error-free, which I guess it
Exactly.
does. Maybe the tolerance of error would be greater than speech in a game of telephone, because it
True.
doesn't matter too much exactly how the flock is moving.
Well, it does. So, for example, if you want to do a coordinated turn,
Yeah.
you want thousands of starlings
To all
to
turn.
turn at the same time.
Yeah.
That is going to take a lot of coordination and
It
error-free.
surely is.
Yeah, and so that's something that people are still trying to understand is how you get these kinds of high fidelity transmission of information.
Okay. Now, when you spoke at the Aspen Science Center's event which took place at the Aspen Center for Physics on the lawn, you said a few things that go a little bit beyond the audience of children, and well, maybe not. Maybe the kids are a lot smarter than I'm aware of.
They
but
were.
they were pretty good, actually.
They did
That-
we
that's-
actually
that's-
did a fun experiments
Yeah,
with that.
I know.
so-
It's a great thing that the Aspen Science Center is doing with these kids. But one of the things that came out of your talk was that swarms sometimes are not totally with co-equal elements. Sometimes there are certain leaders in a swarm that dictate or propagate their concerns to the whole swarm.
That's right.
Could you get into some of that?
Yeah, so that's actually a very interesting topic as well. So how does this goes back to why swarms form in the first place? Actually, a kid in that program gave a very good answer when I asked why flocks and swarms form.
What did he say?
And he essentially said, "Oh, that's when individuals get together to form collectives or societies that are of benefit to all of them." And so, from a biological perspective, that is one of the key reasons why flocks do form. And the benefit could be one of many things. So you could have a benefit that is one obvious one is safety in numbers, right? And so if you have a large number of starlings, there are many lookouts. So you can there's an edge of the swarm that can see a predator approaching.
Okay.
The insides of the swarm are protected, so there's some kind of community benefit. In other species, you have benefits such as heat. This is in penguin huddles. So
sure.
in Antarctica, yeah, that's right. So they come together, and the center of the swarm gets, or the huddle gets very warm.
My limited intuition extended only as far as this. I thought, well, schools of fish. The reason fish school is that if you have a lot of neighbors, your individual chance of being eaten is reduced.
That's certainly
So therefore, everybody would like to be near someone else because your survival is increased.
that is certainly true. Actually,
But it's apparently much more complicated than that.
there could be many different reasons. So in fact, in some fish, in the absence of predators, would be loners, and then when you have more predators, they actually come together, which supports your understanding.
Well,
of it.
you can see that sort of behavior among humans in society, not about getting eaten, but
Right.
about various political maneuverings, I'm sure it works that way.
That's exactly right. And so that comes to the other point that, which is one of the reasons they flock, which we didn't talk about, is experience or knowledge transfer, and that's what you were referring to. So, for example, if you have migratory birds, okay, and so you could have older birds that know the route, and being in a flock allows them to convey that information to juveniles who don't know the route. But there are things like bees.
Bees are a whole separate thing.
Yes.
But do you have anything with bees, or fish would be good
Fish,
too?
I can show you fish.
Yeah. Because I was thinking about the difference between a flock of starlings and a school of fish.
Yes.
Now with starlings, if it's see, the fish form a ball.
Right.
I don't know why, but starlings, if there's a predator, chances are you can only catch one starling per predator. But in the sea, one predator could eat dozens of fish with one gulp.
With one gulp, except that they do actually scatter when they see a predator approach. And I don't believe I have a movie right here, but I can show you later that there are movies where these thresher sharks come and try to attack these kinds of balls of sardines.
But that's remarkable. Why is it spherical? There must be a reason. Except that, I mean, everything is spherical, but why fish?
So this has to do, the shapes of flocks is another interesting thing that we study, which is what influences the shape of flocks. And so there might be other pressures that come from outside that we don't take into account that could account for these kind of toroidal shapes. And, so this is, again, another very interesting
So in the field in which you work, is there a kind of a direction toward producing cures for diseases, or is it much more abstract? I mean, how do you... In astrophysics, people know they want to find out about the history of the universe, and but in something of this kind, what is the direction that guides the whole field of research?
Yeah, so there's very very different kinds of approaches, and so there are people who are more towards the more basic fundamental understanding, and then there are people who are trying to develop, techniques, maybe even therapeutic techniques to control.
Well, for example, do pharmaceutical companies support this type of work, or is it too far out?
It's a bit far out, but robotics is a big contributor. So, and as I showed you before, there are people actually working with robot swarms. And as you know, the Army and the Navy, in fact, are very interested in drone swarms.
Of course.
And they are big contributors to this kind of research as well. And so the interest there, clearly, you could even apply to, we have these driverless cars that are coming on to...
Of course. I meant to ask you, we're almost out of time, but the same analysis, could it be used to prevent traffic jams? It took me 20 minutes to get from Buttermilk into town, and it's because of communication. If all the cars could work, could move in concert, there would be no traffic jam.
That's certainly true.
It's not the number of cars, it's the information transmitted between the drivers.
Right.
So do you have any solutions for
but I don't have any solutions for that. People should drive better, or we should have better traffic lights. No, but seriously, when we transition towards, driverless robotic cars, you can clearly see that this kind of communication between neighboring robotic cars could easily lead to a situation where you have traffic jam free flows of traffic, no collisions, and so on. Well, and so you can think of, you can think of it as a whole bunch of cars being a flock.
Exactly. If they all moved smoothly together and could stop together and start together, it would increase the efficiency of highways, not to mention fuel economy and everything else.
Yeah, so some of the interesting things that we are studying, for example, in the same connection in my lab, is looking at the effects of disorder and disorder and cheating. So what if you have obstacles in this form?
There's no end to this stuff, but I'm afraid we have to wrap it up now. I want to thank my guest, Ajay Gopinathan, who is a biophysicist at the University of California, Merced, and he's here with the Aspen Center for Physics, but we know him because of the good work done by the Aspen Science Center, which is not only directed toward children. I'm kind of hoping that it can cover the entire spectrum of ages.
Yes.
And I think that their future in Aspen is something they really look forward to.
And the Aspen Center for Physics also has programs for
of
the
course.
public lectures
They
and
certainly
discussions
do.
on Wednesdays.
And Wednesdays?
Yes.
Oh, no, it's Thursdays now.
Oh, yeah, that's,
Yeah,
that's
they
the
changed it.
colloquium, but the, yes, you're right.
Yeah,
the
no, it's the
Thursdays.
colloquium
Yeah.
and the public events.
right.
The
That's
Aspen
right,
Center for
that's right.
Physics
Yes.
does public events every Thursday at the Aspen Physics Center. So thank you again.
Thank you.
I'm Cy Coleman, and this is the premiere show of Aspen Science Highlights.